Hello everyone, welcome to section 4.4 on the laws of logarithms. So far we've learned about what a logarithm is. What are they? They're inverses of exponentials. And why do we need them? We want logarithmic functions because we want to be able to solve exponential equations. We need inverses to exponentials. Maybe we want to know how long does it take a certain amount of money to sit into a bank account until it grows to a certain amount of money. I don't know, you're saving up for a Lamborghini. You're going to put maybe 10 grand in a bank. How long do you have to wait till you have maybe 500 grand? Maybe the world is overrun with zombies and population grows exponentially. You want to know how much time to the zombie population matches the population of Bellingham or the population of the U.S. So those are the type of questions we'd like to answer with logarithms. But to be able to solve those type of logarithmic equations, we need to get a little bit more sophisticated with logarithms. We need to learn about logarithmic rules and how to use them to solve equations. Okay, so when I'm writing down these rules for logarithms or these laws of logarithms, they're very similar to kind of the rules we have with exponentials. Exponentials and logarithms are intimately connected, so it's not a surprise that if we have exponential rules that they're actually going to be logarithmic rules. So I'm going to list the logarithmic rules. I'm going to hopefully kind of give you a general way to think about them, and in the next video I'm actually going to prove them to you. So let's recall some exponential rules. So we have these kind of exponent rules. Exponent rules. So for example, let's say we have b to the n times a b to the m. We hopefully learn that what we do in this situation, if we have like bases, is that we add the exponents. Now, I've noticed that a lot of students struggle with exponent rules, but if you are struggling with an exponent rule, I always just try to think about why this is true. This comes from the definition of what an exponent is. What does an exponent mean? It means repeated multiplication. So for example, if I have 2 cubed times 2 to the 4th, what does this mean? This is telling us that I'm taking 2 and I'm multiplying by itself 3 times. And then what are we doing? We're multiplying another 4 2's. So I'm just using the definition of what an exponent means. Take 2, multiply it by itself 3 times. Then take another 2 and multiply it by itself 4 times. Take that result and multiply them together. Well, now how many times am I multiplying 2 together? 1, 2, 3, 4, 5, 6. I'm multiplying 2 by itself 7 times. So that's how this reads. You're taking a number, you're multiplying it by itself n times. Then you're taking that same number and you're multiplying it in an extra m times. So you're really multiplying that number by itself n plus m times. That's a way to think about these exponent rules. Okay? What's another big one? Well, what if we have like b to the n over b to the m? In this case, they'll subtract. So we get b to the n minus m. Why? Well, a simple example, this just has to do with canceling. This just really has to do with canceling. If we, for example, have 2 to the 5th over 2 cubed, what does that mean? It means we have 5 2's in the numerator, and we're dividing by 3 2's in the denominator. Let's just get rid of those secret 1's that are lurking in the bushes. 2 divided by 2, that's just a 1. 2 divided by 2, that's just another one. 2 divided by 2, that's just another one. What are we left with? We're left with 2 squared. So we can think of this, why do they subtract? Well, there's 5 2's in the top, there's 3 in the bottom. I'm canceling 3 2's out of the numerator, so I have 5 minus 3, I have 2 2's left. So they should subtract. Okay, that's another rule. And another important one is if we have, let's say, b to the n to the m. We've used this quite a few times, I think, in this class already. But if it's not clear about why this is true, or if you forget why this is true, just use some numbers and just use the definition of an exponent. So for example, if we have like 2, let's do a 4. Let's say we have 4 squared cubed. Okay, what does this mean? This says I'm multiplying 4 by itself 2 times. So working on the inner parentheses, I have a 4 times a 4. And now I'm taking this group of two fours and I'm multiplying it by itself 3 times. So this is 4 times 4 times 4 times 4 times 4 times 4. So how many 4s do we have in total? 1, 2, 3, 4, 5, 6. We have 6. We have 6. Or you could think that we have 3 groups of 2. This is saying we have 3 groups of 2. We have 3 groups of 2, so we have a total of 6. That's why they should multiply. So here are the famous exponent rules. Here they are. So it's not going to be a surprise. It's not going to be a surprise that exponents have very similar, or logarithms have very similar rules. So, for example, let's talk about log rules. Now, the one thing you should remember that what is a log really is an exponent. For example, if we say, 3 squared is equal to 9, this is equivalent to saying log base 3 of 9. This reads 3 to what power gives you 9? 3 to the power of 2 gives you 9. So what are logs? Logs are exponents. That's what they are. Logs are exponents. Okay. So I'm going to go ahead and erase this. It's a good thing to think about. So now we should ask ourselves the question here. Let's say that we have log base b will be in general of n times m. Of n times m. Well, what happens here? What happens here? Notice over here that this is saying that multiplication corresponds to addition. Multiplication corresponds to addition. So multiplication corresponds to addition. The exponents add. Multiplication corresponds to addition. This is a log rule. This isn't a surprise. If we have this exponent rule, these are kind of inverses of one another. If we have this addition exponent rule, we should have this addition log rule. Multiplication means addition. Multiplication means addition. Similarly over here, what if we do log base b of n over m? Well, division corresponds to subtraction. Division corresponds to subtracting the exponents. So we have that log base b of n divided by m is the same as log base b of n minus log base b of m. I haven't formally proved these, I'm just trying to give you a way to think about them. Exponent rules, multiplication corresponds to addition. Log rules, multiplication corresponds to addition. Exponent rules, division corresponds to subtraction. Log rules, division corresponds to subtraction. Okay, how about over here? Oh, I forgot to write it. B to the n to the m. This is b to the n times m. So we multiply exponents. Similar idea over here. If we have log base b, let's say, and we do m to the nth power, so we have powers are going to correspond to multiplication. So here, this is going to be the same thing as n times log base b of m. Powers correspond to multiplication. Powers correspond to multiplication. That's a way to think about these. What's great about this third log rule I've used here, this one we'll find here soon, is really the star of the show. This is really the star of the show. We'll see this soon. This is the one that's the most important. We'll give it a bunch of stars. This one's the star of the show. You'll see soon. You'll see soon. This one's the star of the show. This says that if in the argument of the logarithm, if we have a power, this power can move out front. That's what this third log rule here is saying. Okay, so here they are. So let's go ahead for right now and let's just do some exercises working with log rules. Okay. Log rules are really one of the most powerful tools. They're not going to go, if you're going on further in math, log rules aren't going away anytime soon. Okay, let's try simplifying. Let's do some exercises where using log rules can help us evaluate logs. So let's go to simplify the following. simplify the following. Okay, and maybe what I'll do here is I'll keep that list of the log rules here on this side of the board. So we know that log base b of n times m, multiplication corresponds to addition. We also have that division corresponds to subtraction. And we also have that powers correspond to multiplication. Okay? So those are our rules. Maybe I'll number them. Maybe we'll number them. This is 1, this is 2, and this is 3. Okay, let's hold on to these. Even though I have them written on the board, you should really have these memorized. Okay, so let's say for example that we have log base 3 of 6 minus log base 3 of 2. Let's see if we can find the exact value of this expression. Okay, maybe pause the video and give this a shot on your own. Okay, let's do it. So what I'm noticing here is, well, first of all, it's going to be tough for us to evaluate log base 3 of 6. It's also going to be hard for us to evaluate log base 3 of 2. Well, what this is saying, this is asking 3 to what power gives us 6? 3 to what power gives us 6? Well, 3 to the first power is 3, and 3 squared is 9, so it's got to be a number between 1 and 2. So the way I'm thinking about it is 3 to the first power is 3, but 3 squared isn't equal to 9. So since 6 is between 3 and 9, log base 3 of 6 has to be a number between 1 and 2. I don't know exactly what number is. This is hard to figure out. Similarly over here, this is saying 3 to what power gives us 2? Well, I don't know. 3 to the 0, anything to the 0th power is 1. And 3 to the first power is 3. So whatever log base 3 of 2 is, 3 to what power gives you 2? Well, it's got to be a number somewhere between 0 and 1. But I don't know exactly what that is. However, for this specific exercise, what we can do, it's actually kind of nice here, is we can use log rule 3. We can use log rule 3 here and say that subtraction corresponds to division. So this is the same thing as log base 3 of 6 over 2. Fun. This is now log base 3. 6 divided by 2. 6 divided by 2 is 3. And now let's think to ourselves, can we evaluate log base 3 of 3? I argue the answer is 1. The answer is 1. Why is this 1? Because what is it telling us? What is this log telling us? Listening. It's saying 3 to what power? 3 to what power gives you 3? And it says 1. Log base 3 of 3 is 1. Log base b of b is always 1. Because b to what power gives you b? 1. Okay, so what was great about this exercise is it was hard for us to evaluate these each separately, but when they were subtracted, we actually realized that the answer is 1. Fun. Let's do another one. So the answer to this one is 1. Okay, let's do another one. Let's say that we are trying to figure out what log base 5 of 5 times root 5 is. Let's see if we're trying to figure out what this is. So we might be able to do this one without log rules. Maybe I'll think about that here in a second. But this is a lesson on log rules. So let's see if we can figure out what this is. Maybe it seems kind of a little bit complicated, kind of everything that's going on here inside the argument. So what we might try to do is maybe expand this. So we could say that this is the same thing, let's see, what rule could we use? Well, notice I'm taking 5 and I'm multiplying it by root 5. So I think we can use log rule 1. So using rule 1 here, we'll have log base 5 of 5 is going to be equal, or add plus log base 5 of the square root of 5. Okay. So here, let's see, what is log base 5 of 5? Or I guess before we do that, I hope you believe that this is just going to be 1. I'll write that in just a second. But a thing to realize here is we can go further with log base 5 of the square root of 5. If we think about this as being log base 5, remember that another way to write a square root is 5 to the 1/2 power. So what we can do from here is we can use, well, which one helps us? Well, I have a power. We have a power. Log rule 3 says I can bring that power out front. So from rule 3, this is the same thing as log base 5 of 5 plus, let's bring down the 1/2, log base 5 of 5. So log rule 3 allowed us to bring that 1/2 out front. Well, now, this is great here. This is great here. So this, what is this saying? This is saying that 5 to what power gives us 5? That's what this is reading. Well, I hope you believe 5 to the first power. 5 to the first power gives us 5. And over here we have a 1/2. So it's 1/2 times, this is asking the same question. 5 to what power? 5 to what power gives us 5? Well, I hope you believe that's 1. So we have 1 plus 1/2 times a 1. Or we have 1 plus a half, which I hope you believe 1 1/2 is 3/2. You could make this a 2 over 2. 2 plus 1 is 3, so 3/2. So the answer to this one here is 3/2. And we used logarithms to do this. However, we actually could have done this problem and evaluated this without using log rules at all for this specific example. Maybe let's explore that idea. I'm going to go ahead and erase what we have here. But the answer here is 3/2. And it was nice to just kind of expand this and evaluate using log rules. Okay, but just maybe a different approach to think about what this is saying. This right here is saying 5 to what power is equal to 5 times the square root of 5. 5 to what power gives us 5 times the square root of 5? Well, I think we can solve this equation by dropping the base. Let's see. Okay, 5 to what power? Well, this is 5 times. This is the same thing as 5 to the 1/2 power. You think of 5 as 5 to the first power. So if we're using exponent rules, this would be 5 to the 1 plus a half. Or this would be 5 would be equal to, 5 to what power is equal to 5 to the 1 plus 3/2. That's 3/2. Okay, what do we do now? We got the same base. Boom. Boom. Dropped a base. Dropped a base. This says that that blank I have here has to be 3/2. So here was another way to think about this problem. What was great is the way we did this problem is one way we said, hey, let's keep this in log form and use log rules. But log rules are very analogous to exponent rules. So I kind of switched this to an exponential form and I used exponent rules and we got to the same answer. How fun. How fun. Okay, let's do another one. Let's do another one. Okay. Let's say that we want to evaluate. Let's say we have 2 times log base 3 of 6 minus 1/2 times log base 3 of 16. Take a moment and see if you can find the exact value of this expression. Let's do it. Okay, let's try to use log rules here. So what can we do? Okay, we need to be a little bit careful. I do see a subtraction sign here. So we eventually are going to need to use log rule 2. But the problem here is when I read log rule 2, notice that for log rule 2, notice that there are no coefficients in front of the logs here. So when I use log rule 2, I have to make sure that there are no coefficients in front of the logs. So I don't like this 2 in front of this log. I don't like this 1/2 in front of this log. Well, how can I get these coefficients in front of the logs out of being out front? Well, here's the star of the show, log rule 3. Log rule 3 allows me to move those inside the parentheses. I can take this 2, and I can write this as 6 squared. I can take this 1/2, and I could write this as 16 to the 1/2. So, using log rule 3, using it twice, we have that log base 3. This is equivalent to log base 3 of 6 squared minus, this will now be 1/2, and we'll get, log base 3, and we'll get a 16 to the 1/2 power. Okay, let's mess around with this a little bit more. So this says log base 3, well 6 squared is 36, minus, okay, notice that 16 to the 1/2 power, what does that mean? That is another notation for the square root of 16, which is 4. So this is log base 3 of 4. Okay, now even looking at these both by themselves, these are hard to figure out. This is saying 3 to what power gives you 36? This is saying 3 to what power gives you 4? Well, I don't know. I don't know. Like 3 cubed is 27. 3 to the 4th, I don't know, whatever 27 times 3 is, it's bigger than 36. It's bigger than 36. I don't know, what would that be? If I multiply another 3, what would that be? 60, what would that be? That would be like another 60 plus another 21. So what would this be? 81? This be 81? Or I should have thought about that. This is like a 3 squared times a 3 squared, and 9 times a 9, 81. Okay. So, well, log base 3 of 36, what is this going to spit out? Well, it's going to spit out some number between 3 and 4, but I don't know exactly what that is. This is hard to evaluate by hand. We'll learn to use our calculator soon. In this case here, 3 to what power gives you 4? Well, I know that 3 to the 1st is 3, and I know that 3 squared is 9. So log base 3 of 4 is some number between 1 and 2. Not really sure what that is. So by themselves, these are hard to evaluate by hand. But for these specific problems, well, I think using log rule 2, subtraction corresponds to division, will hopefully help us in this problem. So using rule 2, we have that this is the same thing as log base 3 of 36 over 4. So I can divide. So this is the same thing as log base 3. What's 36 divided by 4? I think that's 9. So now this is asking the question, 3 to what power gives us 9? I hope you believe it's 2. Or if we just want to be fun, now we're really bringing it up. We're bringing it up, and we're dropping it. Blank equals 2. Drop that base. 3 is 2. I'm sorry. The blank is 2. 3 squared is 9. 3 squared is 9. So the answer to this problem, by playing around a little bit, is we get that the answer to this whole problem, I'm going to erase a little bit of this. The answer to this problem is 2. How fun. How fun is that? Okay. Let's see. Let's do one more. Why not? Okay. Let's say we have log base 2 of 4 times the cubed root of 2. Go ahead and pause the video and see if you can evaluate this one on your own. Okay, let's do it. I think this is another great problem where we could approach this in different ways. What we really are doing in this video is getting used to using log rules. So I'm going to do this problem with log rules first, and I'll show you for this specific example, we could have also thought about this using exponents. Okay, so what can we do here? Well, notice I'm taking a 4 and I'm multiplying it by the cubed root of 2. So this is equivalent to log base 2 of 4 plus log base 2 of the cubed root of 2. So what rule did we use here? We used rule 1. We used log rule 1. Okay, so here we have log base 2 of 4 plus, okay, what do we have over here? Well, this is the same thing as log base 2. Remember, another way to think about a cubed root is think about that as 2 to the 1/3 power. So we have log base 2 of 2 to the 1/3 power. Okay. Okay, well, I guess there's a couple ways we could continue to approach this. Let's see. Let's use log rule 3 for right now. Log rule 3 would allow us to bring this 1/3 out front. So this is log base 2 of 4 will be equal to, let's bring this 1/3 out front. Sorry, plus log base 2 of 4 plus 1/3, and then we get log base 2 of 2. Okay. There's a couple ways we could think about this one. We could just kind of switch this into exponential form. What is this saying to us? This is saying 2 to what power gives you 4? I hope you believe that it's 2. I hope you believe that the answer to this one is 2. 2 squared is 4. 2 squared is 4. So this one is 2. Plus, this is 1/3 times. Well, this says 2. 2 to what power gives you 2? I hope you believe the answer is 1. So a 1 here. So this is a 1. So this will be 2 plus 1/3. So what is that? That'll be what? 6/3 plus 1/3. So what is it? 7/3. 7/3. This answer here is 7/3. Now, just for fun, I thought about this as 2. I thought about this piece right here as 2 to what power gives you 4. The answer is 2. Another way you could have done this, just for fun, all we're doing is having fun. This is saying log base 2. Well, 4 is the same thing as 2 squared. Log rule 3 could have you bring that 2 down. So this is 2 times, ugh, 2 times log base 2 of 2. Well, log base 2 of 2 is just 1, so 2 times 1, we still get out 2. So that's kind of fun. We could have done this a different way. Either we could have thought ourselves 2 to what power gives you 4, the answer is 2. Or if we want to play around with the log rules, well, 4 is the same as 2 squared. Bring that 2 out front from log rule 3. Log base 2 of 2 is 1. We're getting the same answer. This is great. This is fun. Okay, let me show you, instead of using log rules, we could use exponent rules. We could use exponent rules. So this is just a different way to think about this problem, just for fun. This is asking 2 to what power, 2 to what power gives you 4 times the cube root of 2. Well, let's try to drop the base. Let's try to drop the base. What is this? This is 4. How about instead of 4, how about I write that as 2 cubed? I'm sorry, 2 squared. Times the cube root of 2 is the same thing as 2 to the 1/3 power. Well, 2 to what power gives us 2? Well, exponent rules say we add these. So 2 plus 1/3. So we get 2 to, what power? Well, what is 2 plus 1/3? I think we just did that a second ago. What, 6/3 plus 1/3? That's 7/3. 7/3. It's pretty early. We're not going to wake the neighbors. Boom. 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 Drop the base. Drop the base. The blank. I'm sorry, why did I write 2/3 here? 7/3. It's 7/3. Boom. Drop the base. Blank is 7/3. Same answer. Same answer. There's a deep connection between exponent rules and log rules. Okay, I think my notes have another really good example. Let's do one more good example. In the next video, I'll prove the log rules to you. And then we'll do some more exercises. Okay, so here's a last example. This one looks spicy. This one looks a little spicy. This looks fun. The natural log of. The natural log of e to the 200. Ooh, a little spicy, but we can handle it. A little spicy. It's a little. This one looks a little spicy, but it's not too bad. It looks a little spicy. It looks a little spicy. I know it's my best job of drawing a pepper. This problem looks a little spicy. But, you know, a little spice will never kill you. Give it a shot. Alright, let's do it. Let's do it. Okay, so what can we do from here? What can we do? Well, if we're working from the inside out, I guess the question is how do we even read this? Well, what this is saying, this is e to the power of e to the 200. So e is being raised to the power of e to the 200. So if we're working on the inside out, if I'm looking at this inner log, well, the only thing I can think to really try and use here is log rule 3. We can bring this blue out in front of this inner log. So this would be equivalent. This would be equivalent to the natural log of well, maybe I'll write it in blue. Blue. We brought down this e to the 200, and we still now have the natural log of e. Okay, so that was log rule 3. This was log rule 3. Okay, well, now what can we do here? What is natural log of e? What's the natural log of e? What's the natural log of e? Let's do it over here. The natural log of e. Well, remember what a natural log is. This is the logarithm base e. So this is log base e of e. This is saying e to what power gives you e? E to the first power gives you e. So natural log of e is 1. Sweet! Sweet! This is just the natural log of e to the 200. So I just switched colors. But this is just then times 1. This here, wrote it in blue, this here is just equal to 1. Okay? So now we have the natural log of e to the 200. We need to evaluate this. There's 2 ways we could think about this one. I think the easiest way to think about it is maybe just use log rule 3. Log rule 3, again, star of the show, says take that 100 and you can move that out front. So this is just 200. This is 200 times the natural log of e, and we just discovered that the natural log of e is 1, so the answer is 200. Hey, this wasn't so spicy. The answer's 200. Okay, if you didn't want to bring that 200 out front, just think about what this is asking. You know, this is just one approach. Well, natural log of e to the 200, well, that's just saying log base e. This means log base e of e to the 200. So this says e to what power gives you e to the 200? Well, I hope you believe it's 200. Another way to think about it. Okay, that's okay. Not too spicy. We hit it with some milk. We're okay. The answer is 200. Okay, I hope you enjoyed this video. Next video, we'll prove the log rules, and then we'll just get some more practice with using them. Okay, we'll see you there. Take care.